Okay, transformations, part 3. Really nothing new in this one, just different types of problems that we might see. All right, so the first one's kind of going backwards from what we've been doing. What we've been doing is we've been looking at a function and we're describing what transformations were made to that parent function. This time we're going to give you the transformations and you have to write the function. Okay, so for each of these they give you a parent function and then a certain conditions on how it changes. So this first one, absolute value, compression of 3/4, shifted up 4 units and shifted left 3 units. Okay, well, we can just go through this piece by piece. We got the absolute value of x there. Okay, and the first transformation that's listed is that it's a compression of 3/4. Okay, so a compression of 3/4. Remember, compressions, we only do vertical compressions in Algebra 1. So the compression goes out front. So we're going to have 3/4 out front. And then the absolute value of x stays there. All right, the second transformation is that it's shifted up 4 units. Okay, the vertical translations go outside of the function value. Okay, so it's vertical translations are not with the x, it's outside of the x value. So 3/4 x, and then we're just going to add a plus 4 at the end. And the last one, shifted left 3 units. Okay, so this is a horizontal translation. Horizontal translations have to go what we call on the inside of the function. So it has to be with the x part. All right, so 3/4 times the absolute value of x plus 4, and we have to add that 3 inside the function value. So we're going to have 3/4 absolute value of x, and then inside the absolute value bars has to be that left 3 units. Now remember, left 3 units is kind of counterintuitive. Going left, translating, is plus 3. Okay, close the absolute value, and then have that plus 4 at the end for the vertical. That's our transformation. All right, the second one, cubic, x to the 3rd power. So we'll start with that. Down 3, left 1, and reflected across the x-axis. Okay, so again, I'll just go through piece by piece on this one. Down 3 means outside of the cube part, we're going to have to go minus 3. Okay, so we're going to have x to the 3rd minus 3. Okay, shifted 1 left. Okay, now going left and right, you have to be inside the function, so that part has to be part of the cubed part. So how we're going to do that is we're going to do, instead of x to the 3rd power, we're going to have x plus 1 for left 1 to the 3rd power. And then the minus 3 at the end. And then the last part, reflected over the x-axis. Remember, to reflect over the x-axis, you have to have a negative a value. Okay, so there's got to be a negative out front. So we'll just put a negative sign out there. You could put -1, or you could just do the negative sign. I'm just going to do negative x plus 1 to the 3rd power minus 3. All right, quadratic, x squared. So x squared needs to be reflected across the x-axis, stretched by 3, and then shifted down. Okay. All right, so I'll just go through this. I won't do this piece by piece anymore. Reflected across the x-axis means there's got to be a negative out front. Stretched by a factor of 3, there's got to be a 3 out front. Okay, so -3. And then down 2 units. So there's no horizontal translation, so it's just going to stay x squared. And then the down 2 units will be -2 at the end. The next one's exponential. We haven't done a ton of exponential ones. Exponential, the parent function, remember, is 2 to the x power. All right, so where most functions have the inside-outside with parentheses, if it's inside parentheses, it's inside. If it's outside parentheses, it's outside. This time, since our variable's in the exponent, if it's in the exponent, it's going to move left and right. If it's outside of the exponent, it's going to move it up and down. Okay, so this first one shifted right 6. That means we're going to have 2 to the x power. And then in the exponent, in the power, you're going to have -6 to go right 6. Next up is up 7. Okay, so up 7 has to go outside of the exponent. It's going to go at the end plus 7. And then stretch by a factor of 5. Okay. The factor of 5 part, the stretch has to go out front of the parent function. So we're going to have a 5 out front. Okay. So it's 5 times 2 to the x minus 6 power plus 7. Now what you can't do, you cannot make this 10. You can't do 5 times 2 because the order of operations say you'd have to evaluate the exponent first. Okay. So it's separate. So you might see with parentheses. The whole function is inside parentheses and the inside part is inside parentheses. You don't need those, but it's just another way of seeing it. And the last one on this page, compression of 5/4. Now remember, the only difference between a compression and a stretch is a compression is going to be less than 1, and stretches are going to be greater than 1. So a compression of 5/7, this is a square root function, it's a square root of x. So we're going to have 5/7 out front. You're going to have the square root of x. Okay, so that's the compression part. Shifted right 4 units. Okay. Right 4 has to go inside. Well, inside for a square root means underneath the square root. Okay. So if we're going right 4, you gotta go minus 4 underneath the radical. And then last one, up 1, it has to be outside of the radical. Plus 1. All right, so that's writing functions. Again, just go piece by piece. You know where every part's supposed to go. Horizontals have to go inside the function. Vertical translations have to go outside the function. And then the compression, stretches, and reflections go in front every single time. All right, the next type of problem is what if you're given a graph? Okay, so we're given a graph of a function. It's not a parent function, it's just a function, passes a vertical line test. And we're going to transform it in different ways. Okay. Now, if you have a graph, it's going to be handy to kind of mark the important points. All right, now these all have dots. Now remember, the whole line is made of dots. But I'm going to just do these endpoints and the turning points. This dot up here would be -3, 4. Down here would be 1, -1. 2, 3. And then 4, 3. And we're going to transform the function based on those 4 points. Now again, the dots were here, but you could pick any point that you want. All right, so graph the following. F of x, again, f of x was this graph, that's general function graph. And it says g of x equals f of x minus 3. Okay. Now again, minus 3 outside of the function means down 3 units. So what that means, down 3, that affects the y value. So what we're really going to do is we're going to subtract 3 from all the y values. So take all 4 ordered pairs that are up there and just take 3 away from each y value. Okay. So the first point was -3, 4. Okay, well if you take 3 away from 4, you're at -3, 1. The second dot was at 1, -1. Okay. So again, only dealing with the y values because that deals with our vertical movement. Subtract 3 from that y value, -1 minus 3 is -4. So you're at 1, -4. All right. 2, 3, take away 3 from the y, put you at 2, 0. And then likewise 4, 3, if you take away the 3 from the y, you're also at 0. Okay. So the graph holds shape. That f of x is the parent function. And remember that all child graphs have to look like the parent function. Okay. So it's just the original graph shifted down 3 units. So it took 3 away from every y value. The second one, g of x equals negative f of x. So this graph is just a reflection. It's reflected over the x value. When you reflect over the x-axis, what does that change about your graph? Well, it also only changes the y values. Okay. So this time we're going to have our y values are just going to change signs. Okay. So if it's positive, you make it negative. If it's negative, you make it positive. So we're going to flip the y values, okay, or the opposite of the y values. Okay. So x values aren't going to change. Negative 3, 4 is going to become negative 3, negative 4. 1, negative 1, again, just opposite of the y value. It'd be 1, positive 1. 2, 3 will become 2, negative 3. And 4, 3 will become 4, negative 3. Okay. And again, it holds its shape. It's a transformation of the original function. 1/2 f of x. This is a vertical compression. Okay. This is going to compress by 1/2. Now, vertical compression, vertical again only affects the y values. So all of our y values are going to be multiplied by 1/2. All right, so you take the first ordered pair. First ordered pair is negative 4 or negative 3, 4. Okay. So you cut that 4, the y value, in half. So instead of negative 3, 4, it's going to be negative 3, 2. Instead of 1, negative 1, multiply that negative 1 by a half. It's going to be 1, negative half. And then same with those last 2 points. 2, 3 is going to become 2, 1 and a half. Again, x values are not changing, only the y's are being multiplied by a half. And then 4, 1 and a half. So this looks just like the original graph, except it's compressed. It's as if from the top and the bottom, you just kind of smushed it together. All right, and the last one has 2 transformations. It has a horizontal transformation. This is our first one with the horizontal. The +2 moves us left 2. And then the -1 moves us down 1. So every x value, we're going to take 2 away. And every y value, we're going to take 1 away. Because left 2 is going to take away, even though it says plus. All right, so the first point was negative 3, 4. All right, so you take negative 3, and you take 2 away from it, which puts us at negative 5. Left 2 from negative 3 is negative 5. And then down 1 is going to move us to 3. So negative 5, 3. The next ordered pair, which was 1, negative 1. Okay. So it was here. And now from that point, we're going to go left 2 and down 1. Next point, 2, 3. It was at 2, 3. Go left 2, down 1. Puts us at 0, 2. And then 4, 3. Left 2, down 1. Puts us here. Okay. So you could do this from the ordered pairs, or you could do it from the original graph. Connect the dots, and it's just the exact same graph as the parent function, but everything's left 2, down 1. Okay, so that's graphing. You could do all these from the ordered pairs, or you could do all of them from the graph. Doesn't matter. It's kind of helpful to kind of mix and match and do both. All right, in this last set of problems, this first part, we're given a graph of y equals x plus 5 to the fifth, or x plus 5 squared plus 1. Make one change in the original equation so that the graph, and then there's 4 scenarios. All right, so first might be helpful to kind of sketch what the graph originally looks like. Okay. So that is a quadratic that's in vertex form. So we know what it looks like. We know that the vertex is at negative 5, 1. And again, just a rough sketch. And we know it's a parabola that opens up because the a value is positive. So it looks something like that. So what's one change that we could make in the original graph that's going to make it open downward? It currently opens upward because the a value is positive. So if we needed it to open downward, we need that a value to be negative. So we're going to have just the exact same equation, but with a negative out front. That's going to make it open down. Okay. And we knew that already from when we did the quadratics part. How do we make it fatter in part B? Fatter meaning compressed, so it's a wider graph. Well, if you need to compress the graph, you have to multiply it. You have to change the a value, the number in front, to be a number that's less than 0 or less than 1. It has to be a fraction less than 1. Okay. So you pick any fraction less than 1, most commonly 1/2. You could do 1/3, you could do 2/3, any fraction less than 1. So we're just going to do the same exact equation, put a 1/2 in front. Part C has x-intercepts. So that graph currently doesn't have x-intercepts because the vertex is above the x-axis and opens up. So this one has a bunch of different, all of these have a lot of different answers except for A. If you needed to have x-intercepts, one way you could do that is just flip it upside down. Okay. If we had that graph that now opens downward, that's automatically going to give us x-intercepts. Now another way you could get x-intercepts is if you move the vertex down. Okay. The problem with this currently is that the vertex is above the x-axis and it opens up. So if we want to move, we just move the vertex down so it's below the x-axis. How do we do that? Well, we just make the y value of the intercept, the y value of the vertex, negative. So for example, if we do, keep it positive, one change. If we have x plus 5 squared minus 1. That changes the vertex to -5, -1. It opens up, so it's automatically going to have x-intercepts. All right, and the last one, and you can put anything there. You put -1 billion if you want. The last one moves to the left. Okay. Now, if you move to the left, remember, if you're moving to the left in these problems, you're adding to the inside of the function. Okay. If you're adding to the inside of the function is currently +5. So if we're adding a number to that +5, we're going to have a bigger number. So any problem that has a number bigger than 5 inside is going to be left of that original function. Okay. So you can do any number bigger than 5. You can do 6, you can do 7, you can do 10, you can do 100. Doesn't matter. Let's do 7 squared plus 1. Okay. If you wanted to move that to the right, you would have to subtract from that inside part of the function. Because remember, minus h moves it to the right, plus h moves it to the left. All right, and then the last problem is similar to the previous one. This one gives you more specific rules. So they give you a function already. It's quadratic, vertex form. And that first part says to write a function, so that shifts f of x 10 units to the right. Now remember, 10 units to the right, like we just said. If you're moving to the right, you have to do minus that number. Okay? So 10 units to the right, we'd have to subtract 10 from that inside part of the function. So +3 minus 10 is going to give you -7, and then nothing else changes. The second part shifts f of x 5 units down. 5 units down has to go on the outside part of the function. So 5 units down down is subtraction, so we'll have to subtract 5 from that outside portion. Now that's going to just completely cancel out, and we'll just be left with x plus 3 squared plus nothing. All right, reflects over the x-axis. That should say x. It originally said y on your notes. Reflects over the x-axis. That just has to do with the part in front. The part in front is negative. It reflects over the x-axis. If it's positive, it doesn't. So we'll just make that negative out front. Nothing else changes. And then stretched by a factor of 2, that also only deals with the part out front. If you need to stretch it by a factor of 2, you're just going to multiply the front by 2. All right, so nothing really new in that. There's just different types of problems that you could have set up, different scenarios that I could ask.